Lei Wu.
Hi.
Hi. So Lei Wu is a postdoc at PACM of Princeton University. Lei obtained his bachelor degree from Nankai University in 2012 and completed his PhD in computational mathematics at Peking University in 2018. His current research interest focuses on the mathematical understanding of machine learning. Today, Lei will tell us about understanding flow-based models, the representation, landscape, and gradient flow. Now, let me give the control to Lei.
Hi, could you hear me clearly?
Yes.
Okay, good. Thanks for the organizer and for the introduction. Okay, my talk is about the understanding flow-based models, the representation, landscape, and the gradient flow. And it's basically based on our paper. Here's the link of our paper. Flow-based models. Okay, flow-based model looks at the function representation from a continuous dynamics viewpoint. In this model, the functions are generated by a flow map of an ordinary differential equations. Basically, it says that we have an ODE, which with the input, the initial condition is our variable x, and the output is the function we want to represent. So when we choose a different ODE or the right-hand side of the G, we actually get the different functions. This kind of function representation is inspired by the developing of residual networks. So the understanding of this model is highly strongly related to the understanding of residual network as well. Okay, so that's two important questions before we towards understanding of these models. The first question is, what's the correct form of G? Because we cannot choose arbitrarily the function G. Typically, we want to have a simple form of G, and hope that the ODE, the ordinary differential equation, can use those simple function G to generate some very complicated functions. And also, this question is also related to the second question, which is about how to optimize G such that we can our output fx to match the target function or match the training data. So this problem is the two problems is correlated because with the right choice of G, which can make the optimization much easier. With the incorrect form of G, the optimization steps could be very difficult. Okay, that's our motivation of this talk. And here's the outline of this talk. In the first part, I will discuss a little bit about the integral transform-based models. This is basically is trying to answer the first questions, how to choose the form of G. The second part is about the flow-based models. With the right choice of G, we will discuss about the landscape of the flow-based model and also as well as the training of those models. In the third part is the discussion and the summary. Okay, let's move on the first part. So in the classical mathematical analysis, we can represent our function by using Fourier transform in this form. And this form A omega, A omega is nothing else but the inverse transform our target function fx. In this representation, if we discretize it by using grid points, using grid-based methods, which is given in these equations, the problem is that this kind of representation is that the approximation error or a discretization error is typically goes like in this form, which is suffer from the curse dimensionality. That means that the exponent here as divided by d, it explicitly depends on the input dimension d, which goes to 0 when we increase the dimension d, go to infinity. That means this kind of representation is not suitable for the representation of a function in high dimension. But if we tweak the representation a little bit, things will change. For example, if we consider this representation, here the function fx is not the Fourier transform anymore, but it's just but it's still similar. But the integral now is respect to a probability distribution pi. Now pi is a probability distribution. We can use Monte Carlo method to approximate. Let Wj to be MID samples drawn from the pi. Then Fmx is the empirical average of which approximates the target function. Typically, this kind of will give us the Monte Carlo error rate, which is basically the variance of the integrand divided by the number of samples. The good news is that this kind of error rate, which is independent of dimension. That means this kind of representation is more suitable for high-dimensional function representation. Or more generally, we can also consider a more general form, which represents a function, which parameterizes a function f by using a probability distribution rho. Okay, probability of rho. So, but now the difference is that the feature now, the phi x omega is a more general parameterized function parameterized by w. But the model's parameter is actually the probability distribution rho, which is in the rho. Okay, this kind of continuous function representation is well studied in the literature about the theoretical analysis of two-layer neural networks. For example, if we pick up the form of phi in this form, A times sigma B transpose X. Okay, it's a Monte Carlo approximator given in this equation, which is a scaled two-layer neural networks. Here, I emphasize that it's not a standard two-layer neural networks because in practice we never use we typically do not use this explicitly scanning before the function representation before those terms. Another form of G is given by is parameterized by L2 functions. Okay, in this form, the target function is still an expectation with probability distribution pi 0. The difference is that the pi 0 now is fixed, and only the coefficient function at A omega is learnable from the data. This model is this continuous representation is closely related to the random feature model, because if we do the Monte Carlo approximation, then we got this model. Here, the feature or basis function here is random because the bj0 is random sample from the prefix distribution pi 0. So it's random. It's not learned from the data. That's the reason why I call it a random feature model. So with those choices of parameterization, now we can tend to try to write down the flow to optimize our loss function of R. R is a function of A and pi. So typically, there's two types of parameters. A is an L2 function, and pi is a probability distribution. Those two types of parameters will let us to how to use a different type of flow to optimize. The parameter A is L2 function, which is non-conservative. This part can just use a standard gradient flow. Which is basically say that the gradient of A is given by the negative variational derivative. But for the parameter pi is conservative. So it must satisfy intuitively, when we write its dynamics, it must satisfy the continuity equation because it's conservative. And the J is the flux of the continuity equations. And by using the some kind of physical intuition, we can choose a J by using the fixed law that J is pi times the gradient of the chemical potentials. Okay, so in this continuous level, we can write down the flow to optimize the function very intuitively. And it happens that this equation 4 is an ODE, and this ODE is actually the gradient flow in L2 matrix. And specifically for this equation, the equation 5 is an PD, and it happens to be a gradient flow in the Watson-Stein matrix. For example, let us consider the standard two-layer neural networks. Now F is premised by distribution rho. This model can be viewed as infinity-wide two-layer neural networks. And the gradient flow is given in the equation 8. Okay. For this equation, it's exactly the mean field limit of a gradient descent, for two-layer neural networks. That appears in those literature by those authors. And also for the random feature models, if we want to optimize the function AB, we can get the gradient flow given in these equations. It's very simple. It's actually is just a set of ordinary differential equations. So we have the continuous PD or ODE for the optimizing the objective function. Now we can turn to the discretizations. In the equation 10 and 11, we give the continuous model and also the continuous optimizer, which is a PD, given in the equation 11. For this PD, we can, because of rho is a probability distribution, a natural choice to do discretization is a particle method. In the particle method, we replace the rho, we approximate rho t by using a set of particles. The empirical distribution formed by a set of particles, and the dynamics of the rho is determined by the evolution of the particles. The standard particle method tells us that the particle's evolution just follows the velocity field given in these equations. Okay, those is very standard particle discretization for the PD11, and it happens that this discretized dynamics is exactly the gradient descent for the scaled neural network, this one. Okay, this model is more like networks, but the difference is that we have explicit scanning here. So actually, they are different models. They can be viewed in these numerical results. Now we consider two models. One is the conventional, typically used two-layer networks. Another is the one from the continuous viewpoint, which is a scaled two-layer networks. Okay, the two heat maps. The left is the test error for the scaled one, and the right is for the standard conventional networks. We can see that for the model from a continuous viewpoint, it's very robust for the choice of number of parameters or number of neurons. When we increase the number of neurons, the test performance is very robust, does not degenerate. However, for these conventional models, without these scanning factors, the model, we have a large bad area for the test error of this model, especially in the over highly parameterized regime. You can see that when we increase the number of neurons larger and larger, the test error becomes very bad. And the reason is that for this model, when we do gradient descent, in the highly over parameterized, this random feature model actually degenerate to random feature model. This two-layer neural networks actually degenerate to random feature model, but it does not happen for those scaled networks. And okay, we already showed the particle method. So a natural choice is also the smooth particle method to do the discretization. In the smooth particle discretization, we approximate the distribution by using a Gaussian mixture. It's very similar to the particle method. The difference is that we replace the delta function by using a Gaussian density function. And the smooth particle tell us that the dynamics given in the 15, and the 15 is exactly the gradient descent for this models. This model is actually not the original two-layer neural networks anymore, because now the activation function changed. this activation function is actually a smooth ReLU. It's a smooth ReLU. It's a original ReLU smoothed by a Gaussian modifier. Okay, modifier. It can be seen in these pictures. The blue dashed line is the ReLU, and the orange and the green line is the smooth ReLU. Okay, so it's a smooth one ReLU, and also this smooth ReLU has an analytical formulation given in these equations. It has two terms. The second term depends on h. So if we choose h small, this term is negligible. The dominant term is this one. And it happens that this one is actually exactly in the Gaussian area linear units activation function, which becomes a very popular reason, has found lots of application in different problems. So now I will give a very short summary. That's actually about the discretization. So we start from the continuous formulation. Then actually we have two types of discretization. We can first discretize our model and train the model, discretize the model by using standard optimizer like ADAM or SGD. And we can also train the continuous model by design some kind of continuous optimizers like the gradient flow, which is a PD, and try to discretize the continuous optimizers. Those are two types of discretizations sometimes may give us different training methods. Okay. Now let us turn to the main topic of this talk, the flow-based models. This is just let's briefly recall the definition of flow-based models, which is given by this ODEs. So the problem is how to choose the function of G, the correct form of G. Now we have two choices. The first one is we call flow-based random feature models. And this model, we choose the right-hand side by using the random feature model, the continuous random feature models. Well, the distribution pi tau is fixed. It is fixed, and the parameter is a function a omega tau. We call this the flow-based random feature model. And another choice that we can also choose the right-hand side by using the networks model. In these models, our parameter is a sequence of probability distribution, rho tau from 1 to 0, from 0 to 1. Okay, well, in this talk, we call this flow-based as a type of flow-based neural network models. Okay, this model is closely related to the residual network. For example, if we pick up the feature function f the omega w in this form, and we discretize the model by Monte Carlo approximation and Euler fold, we got this discretized model. This discretized model is exactly a residual network, but with a scaling factor before the residual block. This scaling factor is product of the depth and the width. So here, not only the depth, but also the width appears in the scaling factors. Okay, now we have the choice of G. So the next problem is how to optimize this problem. This problem can be viewed as an optimal control problem, and that means that let's introduce some control theory terminology. So in a slightly more general form, we consider the ODE in this form. Here, theta tau is control at tau, and control at tau, and z is the state. So the theta tau in the flow-based random feature models, theta tau is a function. And in the flow-based neural network model, theta tau is a probability distribution. So the control problem is our objective is to minimize loss function over the control, theta tau from 0 to 1. This is our objective function. We try to minimize theta tau such that this loss is minimized. Okay, this is a quite a standard control, optimal control problem. So let us first introduce some control terminology from the control theory. The first one is a co-state P. co-state P has the same dimension of the state Z. Okay, state Z, and also the Hamiltonian. Hamiltonian is a function of the state Z, the co-state P, and the control theta is a function of those two variables, and it's defined by the co-state transpose multiplied by the right-hand side of the ODE. Okay, the control theory tells us that we have those Pontryagin maximal principle for the optimal solution of the problem. Let theta be the solution of the control problem. Then it must satisfy this Pontryagin maximal principle. That means that our optimal control theta tau minimize the Hamiltonian at each layer tau. And the Z tau and the P tau, the state and co-state is given by the Hamiltonian dynamics. Okay, the update, this one is exactly the ODE mean. This is the original ODE. That's the forward update of our state. The update of the co-state is given by these backward equations. This is backward because it starts from the time 0. We have a boundary condition at the time 0, which is the derivative. Okay, this is topology. There should be L prime, which is the derivative of our loss with respect to the output of the ODE. The co-state is linear. It's a linear function. It's not nonlinear. It's linear because this Jacobian is independent of P. Okay, so intuitively we can actually explain the pi tau as the roughly as the derivative of our loss function with respect to the state at layer tau, but it's not exactly the derivative because it's actually the density of the derivative. Yeah, so this is a Pontryagin maximal principle can be intuitively understood as the KKT condition, the first order optimality condition for the optimization problem. This one, okay, because this is a general optimization problem. So we have the first order optimality condition, which is the KKT conditions. The difference is that for this control problem, our feasible variable x is not a vector, it's an ODE. So we have this form of KKT condition, which is given by the Pontryagin maximal principle. With those terminology prepared, let us move to the first models, flow-based random feature models. Okay, first, the flow-based random feature models is, let's first briefly recall, the model is parameterized by this function, those L2 functions. L2 function, which is defined, the norm, L2 norm is defined by these equations. The first proposition is said that the variational derivative of this loss function is given by these equations, which say that the variational derivative is basically the co-state times the feature functions. And the state and the co-state follow the Hamiltonian dynamics, which is the forward propagate update of the Z and the backward update of our co-state P tau, combined with the boundary conditions. Right, this is just a very simple, straightforward calculation will tell us this one. But the interest is that for this problem, we have a very nice property of the landscape. For example, let us first make some assumptions. We have 3 assumptions, which is the first one is that our feature function is continuous in both Z and W. And also our feature functions is bounded and also has a bounded Jacobian, bounded derivative gradient. And the third assumption says that our feature function has a universal approximation property. That means that any linear combination, okay, any continuous function can be approximated by this linear combination of our feature functions. This three assumptions is actually very weak because it can be very easily satisfied by many choice of the feature phi. For example, if we choose the feature function f phi z w by using the standard one, activation applied to a linear transform or affine transform, and choose the activation function by using smooth one like hyperbolic tangent functions, then those three assumptions will be satisfied. Then we have those propositions. Then says that, okay, now if assume our target function is continuous, then we will obtain that any stationary point of those loss functions is also a global minimum, that we have zero loss. Okay, the stationary point here means that the variational derivative of loss functional with respect to the control A equals to 0. Why it happen? We can briefly show a proof sketch. For example, the variational derivative equals to 0 means that this function equals to 0 for any W. That means any linear combination of it also equals to 0. Because the phi has a universal approximation property. So that's we can say that for any continuous function G, we have this term equals to 0. But there's a little bit of problem because G is can be any continuous function, but it's not any continuous function, maybe not any continuous function about with respect to X, because the flow map Z tau X may degenerate. However, by using the second assumption that about the boundless assumption, the feature function has some kind of boundless, then we can, by using the standard ODE theory, we can show that the flow map is non-degenerate. Then this term can be approximately any continuous function of X. And also the ODE theory tells us that P is a continuous function of X. So we can choose G such that, okay, this term equals to this term. Then we got the co-state. This co-state equals to 0 for any tau. Specifically, especially for tau equals to 0. For tau equals to 0, the gradient we know that this P1x is actually the gradient of our loss with respect to output. And because the loss is convex, so the gradient equals to 0 means that this one we must have the loss also equals to 0. So then now we prove the result that the solution must be the global minimum. Okay, the next question is about the gradient flow. Okay, in this for this model, the gradient flow is very easy to write down because we know that
I have a question. I just want to comment that, well, this global the previous proposition you proved is very strong, even in the two-layer neural network without this residual structure case. I think any stationary point of the risk functional may not be a global minimum. I think you need some assumption saying that perhaps limiting the reference measure is supported on the whole.
I will clarify this. I know you're confusing. And this proposition, I only say that the point has 0 variational derivative equals
okay.
Not the stationary point of the gradient flow. I will talk this problem in the next propositions.
Okay, great, thanks.
Okay, so let's move on to the gradient flow. Okay, this gradient flow is easy to write because our parameter now is L2 function, so it will be a standard L2 gradient flow. It's updated. It's just a negative of the derivative. But now let's answer the question of Mason. That okay. So when I talk about the gradient flow, stationary part of the gradient flow, I need to make those assumptions mentioned by Mason that we need to assume that the distribution pi tau is full spot. As full spot, that means the pi tau is positive, non-negative for any omega. And also we make another assumption that the pi tau here is has some kind of continuous property. That means when tau 1 and tau 2 are close to each other, the distribution pi tau 1 and pi 2 is also close. With these assumptions, we can show that the gradient flow of the station of the gradient flow is also the global minimum. Okay, that's the difference. The stationary importance of the gradient flow means the dissipation of our loss equals to 0. That is, this term equals to 0. This term equals to 0. The dissipation equals to 0 does not necessarily imply that the variational derivative equals to 0. So, but if we, with previous two assumptions, this is with the previous two assumptions that we know, we can show that this term is continuous in tau, and also is non-negative. So its integral equals to 0 will give us that it equals to 0 at any tau. By using, and further by using that pi tau is full spot, then we can obtain that the variational derivative equals to 0. Then we, by using the previous proposition, we get the result that this solution is also the global minimum. Okay, now let's turn to the next model, the flow-based neural networks models. Okay, briefly recall the definition of the model. Our parameter in this model is a sequence of probability distribution rho tau. Okay, rho tau. Okay, well now I will try to derive the gradient flow to optimize for these models. Okay, now I provide an intuitive derivation of the gradient flow for by using the Pontryagin maximum principle. The maximum principle tell us that the rho tau is given by the minimizer of this Hamiltonian. So to solve this maximum principle conditions, we can choose, because the rho tau is a probability distribution. So intuitively, we can choose by using the Wasserstein gradient flow to solve this problem for one step. That's the Wasserstein gradient flow for this problem is given in 36. When for a fixed z fixed co-state p, we can evolve this Wasserstein gradient flow to solve this problem. And then we combine the update of the co-state and the co-state, we get this gradient flow. Now, actually, we cannot call this gradient flow, because now we can only show this is a flow, but it may not be gradient flow. But I will come back to this issue in the next slide. Let's just talk about discuss these equations. This is okay. Now this flow is given by the PD. Actually, it's a set of PDs in the equation 37. That for at time tau, the rho tau follows this Wasserstein gradient flow, and the update of z and p is given by the forward and backward dynamics ODE in the equation 39 and 40. So for these flows, we have some very interesting observation. The update of rho tau is independent for each tau when the state and the co-state are given. And the dependence of among the different tau is given by the update of the state and the co-state. Okay, as this combined PD and OD is the flow, and we can actually prove that this very complicated equations are actually the gradient flow, and the metric defined by this integral Wasserstein metric. So our feasible parameter space is the set of sequence of probability distribution. And we define the metric, the following metric. For rho 1 and rho 2, the distance between them is an integral of the Wasserstein distance at each layer tau. Okay, so with this metric defined, then we can prove that the previous very complicated combined PD and ODEs is the gradient flow in this metric space. So now we have the gradient flow for optimize the flow-based neural network models, but we can actually now we can consider the discretizations. So now the PD has two variables. We first discretize the special variable W by using the particle methods. We replace the probability distribution by the empirical distribution formed by a set of particles. By using this particle approximation discretization, we get those ODEs. Okay, now the equations, the gradient flow becomes a set of ODEs. It's not a PD anymore. But still, we actually have two time. One is for T, one is for tau. Tau is the layers, actually the continuous depth variables for tau. We can continuous further to discretize the tau variable by using the standard forward Euler schemes. Then we got the discretize of our model, forward update of our model, and the backward propagation of our gradient. Then the last equation is exactly the gradient descent. Okay, this is the forward propagation. This is for the backward propagation to calculate the gradient informations. And now this is the gradient for the variable W. Then those updates, those equations combined together are exactly the gradient descent for the scaled ResNet, Or in other words, the gradient flow we derive is actually the continuum limit of the gradient descent, of the standard gradient descent for this scaled ResNet, Okay, now we know that we build the connection between the gradient flow and the standard gradient descent method used in practice. But the continuous viewport actually can provide us some other method. For example, and this slide, this slide is giving maximum principle-based training method, which is directly optimize, try to solving the KKT conditions. For this method, assume now we at the step K, we have a control rho tau K. And then we first do a forward propagation to calculate the state and do a backward propagation to calculate the co-state P. Okay, for this method, we actually update the control our parameters rho tau by solving this okay, here it should be argmin, not argmax, it's a typo. For this sub-optimization problem. Because if this convergence, this update converge, then we must have that rho tau satisfies the maximum principle. The last step actually, so because we want to solve this optimization problem to a very small tolerance, typically we can choose some advanced optimizer like LBFJS to solve this sub-optimization problem. This is doable because, okay, typically we cannot use like a second order method to optimize the neural network model, because when we do that, actually we are deal with all the parameters, which is in a very high dimensional. That means in that case, the second order method does not do very well. However, for this is okay. Actually, we decompose the problem for each layers. For each layers, we only update the parameter of the rho tau in here for each layers. This is somehow more lower dimensional. That means in this case, the second method actually can work. And also this method actually introduces some kind of other flexibility. For example, when we want to train a discretized model like quantized neural networks, we hope that the weight of the network is represented by some kind of discrete value like 1 or 0. And in this case, because the weight is not continuous anymore, standard gradient descent does not work. However, in this framework, we can still do it because we can. That in the only difference that we now try to solve this small sub-optimization problem with some constraint that the variable is represented by discrete set. Okay, this numerical results show that. For example, let's look at these pictures. In terms of number of iterations, the maximum principle-based algorithm converge faster than the gradient-based method, like SGD, even ADAM. It's faster, but that does not always mean that the maximum principle-based method is better. Because let's do a comparison between the gradient descent and maximum principle-based method. Okay, in maximum principle-based method, we update the control by solving this argmin, this sub-optimization problem. If we solve this sub-optimization problem very well, we can, the previous numerical result shows that in terms of number of iterations, the row indeed converge faster. However, because this sub-optimization problem probably will take a much longer time to solve because we want to solve it to a very high accuracy. That may take a lot of time. However, for standard gradient descent, we actually only solve this problem, this argmin problem, by using one-step gradient descent. So that means for gradient descent method, the computation cost for each iterations is much lower than maximum principle-based method. But the two methods has their own advantages. So we can try to design some kind of hybrid method to combine, to utilize both of them advantages. So this is one example. Okay, we can propose following two-scale update. That means that we update the control row faster than the updates of the state and co-state. Okay, in this two-scale updates, we assume now we have the state co-state at the iteration k. Then we use this state and co-state to update our control row for big T iterations. Then we update our state co-state use the newest the control row kt. This is a two-scale update. If the t equals to infinity, it recovers a maximum principle-based approach. If t equals to 1, it recovers a standard gradient descent method. So I hope that these two-scale updates can utilize both of the to some extent to utilize both advantages of the two methods. Okay, that's all of my talk. Okay, lastly, I will want to try briefly discuss our viewpoints, the difference between this continuous formulation, continuous viewpoint, and the mean field viewpoint. So sometimes we can show that the mean field understanding and the continuous viewpoint give us the same models, especially for the two-layer neural networks. However, I think that they are very different viewpoints because when we say mean field, actually we start from a discrete model, or the model used in practice, and we try to get some continuous limit or continuous model by taking the limit. It's like the interacting particle in statistical physics, But from the continuous viewpoint, actually we start from the continuous models. And we can consider the different continuous models. And the discrete model is, the practical model is come from the discretization of the continuous models. This is a very standard approach from, in the numerical analysis situations. So this is a continuous formulation allow us to think the problem outside of the box of machine learning. That means that we can actually consider, for example, alternative continuous models. One example is that when we consider the modeling of the training method, and the continuous level, we are not only propose a gradient flow method, we can also directly propose a method based on the maximum principle. That's the this is the method given by the continuous viewpoint. And we can also consider, for example, alternative discretizations. For example, we can, for example, by using different discretizer, typically will give us different models. For example, the smooth particles method actually give us a smooth two-layer neural networks, a smooth two-layer neural network, rather than the original two-layer neural networks with the reload activations. Okay, that's all of my talk. So in the summary, I also want to further to emphasize the viewpoint, the difference of our continuous formulations. So basically, actually, we are trying to formulate the first principle of machine learning, and typically it will give us some new variational and variational like problems, and also the performance of those models is typically more robust to the choice of number of parameters. And lastly, it may give us some new models or new algorithms, which is maybe more suitable for the specific applications. Okay, that's all for my talk. Thank you.
Let's thank Lei for his great talk. Lei, you saved some time, so we have more time for questions. And there are indeed some few questions in the chat box. And let me ask the first question. So how do you choose T in the hybrid approach on slides 46? This is also my question. Did you compare in practice the hybrid method with the gradient descent method? And if so, how did you choose this T, capital T?
Currently, I actually in this talk I only proposed to this method theoretically. I haven't did a numerical test, so I guess I don't have a very concrete answer to these questions. I didn't do any numerical test of this method, yeah. But I guess this kind of method is useful because this allows us to reuse because in this update, for example, in this update 15.2, the state are co-state. Okay, in the optimization of the deep learning or neural networks, actually most of the computation comes from the forward propagation and the backward propagations. And this update, which is pretty fast because the state are co-state is fixed. So during this update, we do not recompute evaluate the computation graph. So this step is pretty fast.
I see. Yeah, I can see the advantage of this hybrid method if these three dynamics are like in different scales itself. So another question is it possible to regularize the problem to have a closed form formula for maximizing the Hamiltonian? If yes, is this training stable?
What do you mean regularize?
I think they mean that, yeah.
Maybe I can ask the question like this. Can you hear me?
Yes.
Okay, great. Yeah, I was wondering because in some cases, if you regularize the the problem, and then the Hamiltonian has like an alternative form where you have a regularization term.
Mm-hmm.
It can happen that the argmax over the expected value of the Hamiltonian has a closed form formula, so that you don't need to use any LBFGS or SGB.
Oh, okay. I answer your question.
Yeah.
Even without a regularization, this problem won't have the closed formula.
It
does not have a closed. It does not have a closed formula. It must be solved by BFGS. So that's the reason why I say that the maximum principle-based method has much more computation cost for each iteration, because I have to use the LBFGS to solve this problem. If I have the closed form, this step will be much more efficient.
Okay, makes sense.
If there are no more questions, let's go to the third speaker.